Okay, good morning, everyone. I'm here today on behalf of my co-authors to report about the preliminary results of the radio occultation campaign that we're doing with LRO, aiming at characterizing the lunar ionosphere. As we know, radio occultations is one of the best tools to characterize the electron concentrations and the charged particle environment around the planetary body. This is due to the fact that the radio signals get perturbed proportionally to the electron content between the transmitter and the receiver. In the past, there have been few measurement campaigns aiming at characterizing the lunar ionosphere, and we have had controversial results because we have had positive detections and negative detections, so non-detections. And the positive detections have shown a weak lunar ionosphere and also a dense lunar ionosphere. When I talk about weak, we talk about something in the order of 1 to 10 electrons per centimeter cube, while a dense one goes up to 1,000. And so we can argue that this dense lunar ionosphere appears to be localized and or episodic. The best observations until now have been obtained by Kaguya, and in 4% of their measurement, they have seen a dense lunar ionosphere, as you can see in the plot there by Imamura et al. 2012. And on the day side, and this is important, we will talk about that later, they've seen, as you can see in the plot, their concentrations up to almost 500 per centimeter cube. So the question that we have is we want to characterize the lunar ionosphere, and to do that we want to gather many measurements in different observation conditions, so different altitude locations, local time, solar zenith angle, and also different solar activity. Lunar Reconnaissance Orbiter has been orbiting the moon for 14 years now on orbits that lately have been with a period of almost 2 hours. So it's a very well-placed asset to gather this kind of observation. A question that you may have is why LRO hasn't been able to observe this occultation until now, and this is mainly due to operational difficulties and limitations. As you can see in the sketch there, the blue shaded area shows the region where the contact with Earth can be established. So you can see that when the spacecraft goes into occultation, the Earth direction goes outside of that, so we cannot establish a link with the Earth. There are two possible solutions to this, and the first one is to just allow a wider angular separation between the antenna bore site and the Earth direction. The other solution is to actually move the spacecraft, maneuver the spacecraft and execute a spacecraft slew. This way we will have the Earth in the, again, antenna bore site direction. Both solutions have pros and cons. In particular, the first one is the easiest one because it does not require to maneuver the spacecraft to change the operations. But on the other side, in this way, the Earth direction is way off bore site of the antenna, and this implies a higher noise in the data and a very strong phase perturbation. Without a proper calibration, this data is not usable. The second solution is a little bit harder to implement because it requires a cooperation and organization with other instruments and to maneuver actually the spacecraft. But on the upside, this allows us to keep the same pointing geometry as when we are doing nominal tracking. So from the data analysis standpoint, it's way easier. Here we show the results that we obtained with the second approach, but keep in mind that these are in a small number with respect to the total number of the observation that we could gather, because roughly speaking, the ratio is 5 to 1. I will not go into the details of the data analysis, but please feel free to ask or to catch me at a break. So here we have analyzed the data from April to May 2022, and we have seen both dense positive detections. You can see that here we have a plot of the electron density versus the altitude, and this corresponds to roughly 1,000 electrons per centimeter cube. And we've had in the same period also non-detections. This is on two arcs, two observation arcs, but on two other arcs we have very similar results. Again, you can see that we get detections, positive detection of a dense lunar ionosphere. This is here it's particularly interesting because on these 5 consecutive days we had many slewed passes separated by 2 hours one with the other. This means that the trajectory of the probe is substantially unchanged in the same day from 2 hours to the other, And so we are probing substantially the same point in the lunar ionosphere. The red boxes indicate a non-detection, the green ones a detection. So you can see that in the time span of 2 hours, we can have a dense lunar ionosphere, or we can have the absence of an ionosphere. Another very interesting fact you can see on the right side, I reported the local solar time, LST, and many of these positive detections have been obtained on the night side, in contrast to many previous observations, but compatible with a recent surprising report by Chandrayaan-2, where they observed a dense lunar ionosphere on the night side. We have tried to tie these observations to the environment, in particular to the solar wind. You can see in the plot on the right, we have the 3 first panels that report the proton and electron energies, and then we have the solar wind magnetic field. The red vertical lines indicate the detections, the gray the non-detection, and the red dotted line indicates the strongest detection that we had. In that case of this last one, the strongest one, we can see that there is a clear correlation with the passage of a dense solar wind stream. However, for the others, we couldn't find, and we still cannot find a clear one-to-one correlation. We are investigating other mechanisms that can be behind this, but we need to gather more data. So just to conclude, we have seen and we have shown that we can have electron density and total electron content values in a fixed location on the lunar ionosphere, changing by increasing and decreasing by 1 order of magnitude on a 2 hours time span. In contrast to almost all prior observation, we have seen a dense ionosphere on the night side. However, the data that we have until now is not enough to fully characterize this effect and the mechanism behind it. However, this is a work in progress, because until now we have analyzed around 60 profiles. We have tens more that are being analyzed right now. And however, as I said at the beginning, we are not yet analyzing the data that has been obtained when we are not slewing the spacecraft. We are putting a lot of effort in developing a robust and efficient phase calibration. This way we could add also this data to the analysis, raising the total number of occultation to hundreds. So this is it. Thank you.
All right, thank you very much. We have time for a couple questions, and I'll actually start with one in the chat from Peter Chi that says, were any of the ionospheric events detected when the moon was in the magnetotail?
Sorry, I didn't get the last part.
When the moon was in the magnetotail.
We are looking into that. We had both, actually.
Okay, the results you showed here then were for just the solar wind?
Actually, we have tried to explain it with many different explanations. This was the one that I showed about solar wind is just one example. We have tried also to check correlations with meteor showers and other effects, but we still don't have a clear answer. So I don't want to expand too much on that.
Certainly. I'm just trying to clarify, were your observations only in the solar wind, or were they also taken during the magnetotail crossings?
Both times.
Okay. It looks like we have one question in the room. If you come use the microphone, then those online can hear.
Hi. Hello, my name is Sophia Westerkamp. I was wondering that it says kind of on your conclusion slide that in contrast to a lot of the other prior observations, you detected the dense ionosphere on the night side of the moon. And I was wondering if you could hypothesize why kind of your methods may have detected this ionosphere where other methods have not.
Yes. So first of all, there is one thing that I forgot to clarify. The horizontal resolution of our data is around 460 kilometers. That corresponds to 15 degrees in the solar zenith angle. So in principle, some of the observation that we had on the night side indeed may be around the terminator. So there could be some cross-terminator transport. The reason why we have seen this, and we are particularly, this data, in my opinion, is very interesting, is that we had observation that were, in particular, the ones on the 5 days that I've shown are exactly identical. The observation geometry, the spacecraft attitude, the data analysis, exactly identical for all of them. And we can see, and it's actually the LRO data is pretty well placed because it is in S-band, so it's very sensitive to this effect. And we have a very good orbital reconstruction. We are a very good gravity field for the moon, so we can draw a very precise orbit of the spacecraft. And so the data is actually pretty sensitive to this effect.
Great, thank you so much.